Hello, and welcome to this lecture from the School of Computing at University Utara, Malaysia, led by Dr. Ala Jabbar Al-Maliki. We are examining a critical vulnerability in how the world secures information. Most modern digital security relies on RSA and other mathematical algorithms to shield everything from private messages to banking infrastructure. These systems assume that the computational power required to break these codes is simply out of reach. Quantum computers change that assumption through a process called superposition. This allows them to process massive amounts of data simultaneously. While a classical supercomputer might take billions of years to factor the large prime numbers protecting your data, a quantum computer running Shor's algorithm could theoretically find the solution in minutes. This creates an immediate risk known as harvest now, decrypt later. As shown in this diagram, adversaries are currently intercepting and stockpiling encrypted data. They are waiting for the moment they possess a quantum processor powerful enough to solve the math and reveal the contents. This threat targets any data with a long shelf life. For healthcare records, valuable intellectual property, or state secrets that must remain private for decades, today's encryption is already insufficient. Once a capable quantum machine exists, the information we are saving right now can be exposed instantly. Defending against this requires a shift from mathematical security to physical security. This is quantum cryptography. Instead of relying on a difficult math problem, we use the laws of physics to achieve information-theoretic security, a level of protection that remains intact regardless of how much computing power a hacker possesses. The system relies on the principle that observation causes perturbation. Notice the photon wave in this model. In quantum mechanics, it is physically impossible to measure or observe a system without changing its state. The moment an external observer attempts to interact with the photon, its path and shape are altered. We can use this physical law to build a communication system where any attempt to spy on a key exchange is immediately detectable. An eavesdropper cannot simply listen in. Their very presence introduces errors that provide undeniable evidence of a breach. We can see this in action through quantum key distribution, or QKD. In this logical grid, Alice wants to send a secret key to Bob, one bit at a time, using single photons of light. Look at rows 1 and 2. Alice encodes each bit by changing the photon's polarization, the direction the light wave oscillates. She uses two different codebooks, or bases, a rectilinear base, shown as a plus sign, and a diagonal base, shown as an X. For every bit, she makes two random choices, the bit value and the base used to send it. When Bob receives the photons, he doesn't know which base Alice used. He has to guess, as shown in row 3. If he happens to choose the same base Alice used, he measures her bit correctly. If he chooses the wrong base, his result will be entirely random. After the sequence is sent, Alice and Bob use a public channel to compare only the bases they used. Note how the grid strikes out the columns where their choices didn't match. They discard those results, leaving behind a shorter, identical string of bits. This is their shared secret key. Now consider the eavesdropper, Eve. If she intercepts a photon, she also has to guess a base to measure it. Think about what happens to the physical state of that photon before it reaches Bob if Eve guesses the wrong base. Because Eve measured the photon, she changed it. Even if Bob then uses the correct base, the bit he receives is now randomized. In row 4, the result turns red to indicate this error. Eve's attempt to observe the key has introduced a measurable discrepancy. By comparing a small sample of their final key bits, Alice and Bob can check the error rate. If the errors are above a certain threshold, they know someone was listening. They scrap the key and start over, leaving the spy with nothing. It is important to clarify that QKD is used specifically to share the key, rather than to encrypt the entire message. The physics-based block shown here focuses entirely on establishing that initial secret without it being intercepted. This creates a hybrid system. We use physics to exchange the key, then feed that key into fast classical algorithms like AES 256 to encrypt large-scale data. This approach combines the high speed of traditional encryption with the security of a quantum-resistant key exchange. These systems are currently being deployed. The Messias satellite, launched in 2016, demonstrated intercontinental quantum distribution. On the ground, researchers have successfully sent quantum keys across 120 kilometers of optical fiber, which is the scale needed for metropolitan networks. However, physical constraints remain. Single photons degrade over long distances in fiber, and because we cannot measure them without changing them, we cannot use standard amplifiers to boost the signal. Overcoming these distance limits requires new hardware, like quantum repeaters, to bridge the gaps between cities. Understanding these developments is a requirement for anyone working in modern cybersecurity. If you found this breakdown of quantum distribution helpful, like this video and subscribe for more deep dives into complex computing. Mathematical defenses that seemed impenetrable for decades are now facing a countdown. Quantum cryptography offers a different path by grounding security in the mechanical behavior of subatomic particles. It creates a system where the very act of spying leaves a permanent physical record, ensuring our most sensitive secrets remain protected by the laws of the universe.